Hello, this is Concrete Path, and this lecture would be for getting the influence line diagrams related to that truss members. So we need to get the member forces, and firstly we need to get the ILDs. How you draw that influence line diagram for different those truss members. Let's go for that. And this lecture will be dealing with the analysis. How can you get the entire ILD at each ordinate? So it's saying that ILD for trusses, and it's not any short tricks. We are going for the analysis here. This is the analysis, and it says that if you have this truss, you need to get the ILDs for truss members. So we say that we already saw that what was the load path for the floor girders. Load path. That load was going from that deck plates to that stringers. From that we had that floor beams, and after that finally we had cross girders, and finally we had abutments. This was the load path, and that similar fashion is also here. Now we say that we are applying load only at the joints for the truss. If you have any general truss, I would say you have to apply the loads only at the joints. So loads applied at joints. So that means if you talk about any particular member, we might be having some critical points. Where we apply loads, and we need to get the ordinates at those critical points. And finally then we can draw that. We can join them by a straight line, and that would be your ILD. So similar to that of a floor girder. So we need to get the ordinates at those critical points, at those joints. In that case, we said that the joints were panel points, and in this case we say we are applying the loads at the joints. So we need to get the ordinates at the joints, then after that join them by a straight line. Let's go for the problem 1. Let's take the first problem of that ILDs. So we have this truss, we have this truss. This is your truss member. This is your truss. 1 2 3 4. 1 2 3 4. In this fashion. 1 2 3 4. 1 2 3 4. So let's say we have a support here. We have one more support here. Support A, support B, and the length is 6 meter. This is also 6 meter. This is also 6 meter. This is also 6 meter, and the height is also 6 meter. Height equals to 6 meter. Height is also 6 meter. Now we have one member that we call it as member GB. This is member GB. Let's say this is E. We can call it as GE. So we need to draw the ILD for this member force. ILD for GE member. ILD for this member GE. So let's go for this. Now load is moving. I would say load is moving. So if I solve for those joints, what are the joints we can have? If I say that load is moving in this way from the bottom, I would say loading joints are A, E. Let's say this is some C, this is D. Loading is we have to apply the loads at those joints A, E, C, and D, and B. Then we say what is the value of that? What is the ordinate of that ILD for the GE at those joints when load was at those joints? Accordingly, I had to join those ordinates by straight lines. Now let's take the first point that the load was at point A. Now if I take that point, load was at point A. If the load was at point A, this is your point A. That means entire load gets transferred to the support. Would there be any force in the member GE? Would there be any force in the member GE? If I cut the section, I have to cut the sections. If I cut the section in a way that our unknown is only that, in such a way that that analysis for that unknown is easier. If I cut the section in this way, that means I am left with this part, and I am left with this part. There might be some force in this one also. There might be some force also in this one, and there might be some force also in this one. So this is our unknown. Let's say this is some F. We are talking about this one. That's your GE. So I would say if I apply summation of forces in y direction, I would say one is downwards and one is upwards, and there is some f also component of that, f sine theta upwards. I would say that equals to 0. That means f is 0 for this part. So when the load was at point A, your ILD for your GE, that ordinate was equals to 0. Now let's take the second case, that load was at point E. Now the load was at point E. Let's remove this one. Now second case is that load is at point E. If the load is at point E, at joint E, so load is here. What is the reaction we can have? What is the reaction? Can you tell me what is the reaction? If the total length is 4 meter, if the total length is, let's say this is 6 plus 6 plus, if the total length is 24 and load is applied at this one, that's 1 by 4. So reaction here would be 3 by 4 and this reaction would be 1 by 4. So reaction is equals to 3 by 4. So the reaction here is equals to 3 by 4. Now if I cut this section, I have to maintain the equilibrium. I would say your summation of Fy goes to 0. I would say your 3 by 4 is upwards, and we have negative downwards 1, and we have upwards f sine theta. If this is theta, I can get the theta, I can get the sine theta also. If this is theta, I would say this component along the vertical, that is f sine theta. That equals to 0. I would solve that. I would say 3 by 4 minus 1, that's minus 1 by 4. And finally, I would get a positive value of 1 by 4 equals to f sine theta. Can I get this? 1 by 4 f sine theta. Now, if I say what is the value of sine theta? What's the value of sine theta? I would say sine theta would be, if I take any, because of the symmetry we have, you can take any rectangle. I would say this is some theta, and we have some 6 meter here, and we have some height of 6 meter. So sine theta, that's perpendicular by base, that is same, that's 45. That means tan theta is 45. That is theta is 45. So finally, I would say sine theta is perpendicular by hypotenuse 6 by root of that 6 square plus 6 square. That means sine theta is 1 by 2, 1 by root 2, because theta is 45. And that's also, we call it as diagonal. We call this diagonal as d, and there is some height of h. So sine theta is actually h by d in a general way. If I represent it in terms of general way, I would say this is some h by d, this is some h by d. So that's your f into h by d. And then finally we say your f equals to that 1 by 4 d by h. Or we also say that this is 1 by 4 cosecant theta. 1 by 4 cosecant theta. Is it 1 by 4? 1 by 4 cosecant theta. Then if I substitute that value of what you have, that cosecant theta, we got that value of that was root 2. So if I say root 2 into, that is root 2 into 0.25, that's 0.3536. So the ordinate finally equals to 0.3536. This is the ordinate we have, 0.3536. 0.3536. Let's forget that. So we have the ordinate, that's positive 0.3536 when the load was at point E. Now third thing is that when the load is at point C, when the load is at point C. If the load is at point C, can you tell me what is the reaction? Third thing is that, third case, that load is at point, that's at the mid span of this beam. If I say that there's some beam, load is at mid span, I would say the reaction would be 1 by 2. So reaction A equals to 1 by 2. So if I say reaction is 1 by 2, if I say the reaction is 1 by 2, and I have to cut the section here, that means load is here, there's no effect of this load now in the calculations, because I am cutting the section only up to this part. So only the reaction A is here, and there is some component of that F along the vertical. So I have to balance those two only for this case now. So let's have that now. Let's have that. I would say if I apply summation of forces in the y direction, that's equals to 0, I would say reaction of upwards 1 by 2 and plus f sine theta. Is it h by d? Yeah. Some sine theta, f sine theta equals to, that's equals to 0. That means f equals to 1 by 2 d by h negative. 1 by 2 d by h negative. That is equals to, finally you would get value of 0.7071. That's negative, 0.7071. 0.7071. So that's when load was at mid span at joint C. So you got a value of 0.7071 somewhere here, 0.7071. that we also represent by xd by lh. Let's have that 0.7071. After that, you have to apply the load at point D. Actually, there's no need. Actually, there is no need now. If you got this, if you got this panel, if you got the GE, you have two critical points. One is your point E, one is your point C. If you got the ordinates here, then finally you have to join them up to the point A and B, such that your diagram finally would have been in this way. It would have been in this way. The final diagram is actually in this way. Now, if you want to still calculate that, if the load was at point D and if the load was at point E, I will show you that also. Now, if I said if the load is at point D, if the load is at point D, if the load is at point D, can you tell me what is this direction? Would that be equals to that's 1/4? Would that be 1/4? I think that would be 1/4, and this one would be 3/4. So if the reaction is 1/4, and I'm cutting this section, so this is reaction of 1/4, and I would say there is no, this was also not there. I would say 1/4. This is 1/4. This is 1/4. So I would get an ordinate of this one divided by 2. So finally, that's also equals to 0.3536 negative 0.3536 0.3536. That's same, because here the ordinate, this length is 6 meter and this length is also 6 meter, and the slope is same, this ordinate is, actually we write, say this is xd by l in xd by lh. So if I say what is this value of x, if I directly now say what is this value of x, I would say this value of x for this one is in this direction. This is the value of x, and for this ordinate, this is the direction of x, and for this direction ordinate, this is the value of x, and x, this is the value of x. If I have that value of x equals to 6 meter for the first point, and your diagonal value of diagonal is equals to, we know that diagonal equals to 6√2. Can you say 6√2? 6√2 divided by L, total length of that L equals to 24 meter, and your h, or that height of that truss, that's also 6 meter, and you would finally get value of, a value of 1/4 of that √2, 1/4 and √2. So that would be equals to this one, 1/4 of that √2, 1/4 of that √2. That's 3.3536. So this is the equation for that. It is similar to that of if you have a simply support beam, and you need to get the shear at any section. Let's say this is some section x, and this one is your L minus x. I would say the shear force ILD is in this way. This is x by L, and this one is your that is what you call as L minus x by L. So this part is similar to that, x by L. In this equation we have xd by L, xd by LH, xd by LH, and we have this factor of that d by h also here, d by h, x by L into d by h. That's your it's accounting that the member is it's a diagonal member, because your member was actually a web member. That's your diagonal member. So to account that effect, we have some height of h, we have some that diagonal length of d. So that to account that, so we have this factor of d by h also here. Okay, this is the first problem, and let's go for the second one. Let's go for the second one now. Let's go for the second one. Let's go for the second one. It's saying that get the member force U2, U3. ILD for this member force U2, U3, while your structure looks like, truss looks like, I would say this is your truss. 1, 2, 3, 6, 7. 7 ordinates, 6 ordinates. Let's say this is your let's say this is U1, U2, U3, U4, U5, U6, U7. Upper chord members, U2, U3 is your upper chord member. We call it as upper chord member, upper chord member, one of the upper chord members. And on the bottom we say L1, L2, L3, L4, L5, L6, L7. Now we have to join those. We have to join them by diagonals. We have diagonals also in this way. Then up to the midspan, then there is change of that fashion. There is a change of fashion. So that finally it's in this way also. So this what we call as N girder. This is N girder. Here the shape is N girder. So we say this is your N truss, N type truss, N truss. Let's say this is N truss. Okay. Now we need to get the member force ILD for this member U2, U3. You need to get the ILD for this one U2, U3, U2, U3. So we have to apply that. Let's say the loading is from this bottom. Let's say the loading is through type. We call it as through type. Let's say the loading is through type. Let's say that loading is through type. We can assume it. Loading is through type. Loading is going in this fashion. Now we have to apply the loads only at the joints. This is the thing. We have to apply the loads at the joints. Then after that, we need to get the ILD ordinates at those joints and finally join them by straight line. Let's take the first case that load was at L1. If the load was at L1, can you tell me what's the member force we can have? What is the force in the member we can have? If this is L1, load is applied at this joint, there would be reaction of 1. Can we say that reaction would be 1 here? If I cut the section, let's say, I would cut the section in such a way that that calculation of that member force would be easy. So I would cut the section in this way. If I cut the section in this way, I am left with the section as some sort of this one. There would be some force, and there would be some force in this one also, and there would be some force in this one also. Now we have to do one thing. Our unknown, which one is your unknown? Out of these three, which one is your unknown? I would say there is an unknown of F in this one. So this one is your unknown of F. So I would say you have to ensure that how can you get this value of F? You have to keep other two in such a way that their effect is we don't have to account their effect. I would say if I extend this, they are going somewhere. Their direction is somewhere. They are meeting somewhere here, and that's your L3. That's your L3 where they are meeting. If I apply moments, summation of moments at L3 equals to 0, I would get only effect of this F. So I have to ensure that also. Now, based on this one, you are applying load at what you call as L1. What would be the force in the F? Can I say that would be 0? Because I would say this is 1 into some length of, let's say the panel length is, let's say the length here is A. So total length is L equals to 6A. Panel length is A. This is the panel length A. That means if I write that 1 into 2A and minus times 1 into 2A, one is clockwise, next one is your anti-clockwise reaction. Then I would say then we have some clockwise of F into some horizontal vertical height H, that equals to 0. So F equals to 0 for the first point. So let's have that ordinate, first ordinate. When the load was at L1, that means ordinate was 0. That means force developed in U2, U3 was equals to 0. Now second case is that when you apply load at L2. Now second case, right, load is at L2. When the load is at L2, that means load is somewhere here. Or we can, if the case was that load was from the top, we call that loading on the deck. If the load was here, so we would have also solved for that also. Let's say that load was at this one, at this location. Can you guess the reaction? Can you get this reaction now? Can you get the reaction here? What should be the reaction at L1? If we have six segments and load is at one of the segments, so if this is a beam of 6A and load is at A from support A, so this would be 5/6 of A. This would be 5/6 of that load 1. So this is the ordinate we can have, 5/6. Can we say that this is the 5/6? So the reaction here would be 5/6. Now we have to say you apply moments, summation of moments at L3. So if I apply that, I would say your reaction of 5/6 into 2A, that's clockwise. Is that clockwise? Yeah. and then we have anti-clockwise about the point L3. So minus times 1 into A, minus times 1 into A, and we have that clockwise of F into H equals to 0. So I would say that force in that member equals to that 5 by 6 into that's 10 by 6 minus 1, that's equals to minus 2 by 3. So finally you got this value as minus 2 by 3 of H, minus 2 by 3 of H, minus 2 by 3 of L by H, minus 2 by 3 of L by H, where your L is actually 6A, where L is actually 6A, where your L is actually 6A. So you got this value, or you can solve it in terms of A. I would say you have this 10 by 6 minus 1. So you got this value of 2 by 3, 2 by 3 of if I write it in this way also, I would say you have this ordinate 5A by 6A, and you have this one length of 2A, then minus times 1 into A equals to F into H minus times. So that's finally we got that value of 2 by 3 of A by H. I can say 2 by 3 of A by H. Would that be equals to 2 by 3 of A by H? Yeah, 2 by 3 of A by H. 2 by 3 of A by H, not L. L is the total length of 6A. So 2 by 3 of A by H you can write. 2 by 3 of minus times 2 by 3 of A by H. Minus times 2 by 3 of A by H. So the ordinate is minus 2 by 3 of A by H. Let's say the ordinate here is somewhere here. Minus 2 by 3 of A by H, negative. Then after that, load is applied at L3. Load is applied at L3. Load is applied at L3. If the load is applied at L3, can you get the reaction? Can you get the reaction? Can you get the reaction? Now load is not applied at L2, it's applied at L3, and L3 is out of the section. So when we are applying, when we do summation of moments, so effect of that would not be there. So let's write the equation now again. Let's write the equation again. I would say load was somewhere here, and it's out of that section, and load was here. So I would say your reaction would be 4 by 6. Can we say that reaction would be 4 by 6? Load is here, this is 2, this is 4, and reaction here would be 4 by 6. So reaction is 4 by 6. That means 4 by 6 of length is 2A ordinate. So minus times would there be any other thing? There is no any other thing. So this part is equals to this one. So finally I got that negative value of F equals to, that's 8 by 6, that's 4 by 3, negative times 4 by 3 A by H, minus 4 by 3 A by H, minus 4 by 3 A by H. So there's some ordinate, minus 4 by 3 A by H, 4 by 3 A by H. This is also negative. So actually we needed only these two critical points. Once you got these two critical points, because your U2, U3 was between those critical 2 points. U2, U3 was between those critical 2 points. Once you got those two critical points, you had to join finally the ordinates such that they are joined by a straight line. So if I say that final diagram would be some sort of a triangle, some sort of triangle would be there. Once we got one of the ordinates here, so finally I have to join them straight line such that your diagram would be in this fashion. You have to ensure that, see, in this what you call as trusses, you might be having some member force. Let's say this is a vertical member force, and it might be having connected with two triangles. It might be having connected with two triangles. So we need to see whether we have two critical points, whether we have three critical points. We need to see how many critical points we have. If you talk about this member, this one, we have three critical points here, three critical joints. So we need to only calculate what is the ordinate here at these three critical points. Then you join them finally. And if still you want to get, if you want still that, I want that what are the ordinates at these two critical points also, L4, L5. At this one and at this one, you can solve that one also, because your reaction is getting changed and there is no any other force in this section. So if I say load was at L4 now, if the load is at L4, if the load is now here, I would say reaction would be 1 by 2. That's 3 by 6, that's 1 by 2. So reaction would be 1 by 2. If the reaction is 1 by 2, if the reaction is 1 by 2, or we can say 3 by 6, so you can write 1 by 2, that's balanced by that. So finally you got a value of, that's 1 by 2 of 2. That's let's say that you have that reaction of 1 by 2, or we can say this is 3 by 6, 3 by 6. So if I write that 3 by 6 into 2a plus fh equals to 0, so I would get 6 by 6a, 6 by 6a. Yeah, that's actually 3, yeah, 6a by 6a, that's 6a by 6h. So finally a by h minus times a by h. So if this was if this was 4 by 3, and that one would be 3 by 3, we can say that's 3 by 3 a by h, or that's also equals to minus times a by h. And finally this one would be by the symmetry, I would say this one would be also, once you got the reaction of final, if the load is at now L5, if the load is here L5, so the reaction, this one would be 4 by 6, reaction would be 4 by 6, I would say this is 4 by 6 into 2a, that's 8 by 3, that's 4 by 3. Now reaction would be only 2 by 6, sorry, reaction would be 2 by 6 now. If the load is at L6, you can say reaction this one would be 2 by 6, so that's 1 by 3. 1 by 3 of 2a, that's 2 by 3, so the ordinate would be 2 by 3. And similarly after that, one more joint is that load is at L6, load is at this point now, reaction would be 1 by 6. This is 1, so reaction would be 1 by 6, and then we say 1 by 6 of 2a plus fh equals to 0, then you can get value of, that's 1 by 3 a by h, 1 by 3 a by h. Then final one more ordinate would be somewhere here, 1 by 3 a by h. And finally at the last point, that your reaction at a would be 0, because if the load is at L7, reaction here would be 0, so you would say 0 into sum 2a into plus fh equals to 0, so ordinate would be 0. So this is your BMD, that ILD for that force, member force U2 U3. U2 U3. See, in the truss members, we are not solving moments, we are only calculating the member forces. It may be compressive or tensile. We are solving for member forces. It can be compressive or it can be tensile. Axial forces. Yeah, that's your member forces. Let's take the third problem of those ILDs. Let's take the third problem that we have a through type truss. We have a through type truss 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 5 panels. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's say there's some support A, support B, and I would say length equals to 5 times A. Let's say this is the panel of length A. Panel of length A, 1, 2, 3, 4, 5. Okay, and there is some height of H. Let's say there's some height of H, and there's some diagonal of H. There's some diagonal of D. D is your diagonal. Now the thing is that you say that theta is 45. Theta is 45. And all those triangles are similar. Theta at every point is 45. That here the theta is 45, theta is 45. This is 90. You can say this is 90, and this is 90. Theta is 45. Let's go for that. Let's go for that now. Let's go for that. Let's go for that. Theta is 45. We need to get. We have these members. We call them as ACD PQR. ACD PQR. ACD PQR. And we need to get the ILD for, you need to get the ILD for, ILDs for, let's go for CD, let's get for QR, and let's get for QC, let's get for PA. CD, QR, QC, PA. Let's go for the first case, that's CD. Let's take the CD member. Let's take the CD member. Let's take the CD member. I would say you just copy it. Just copy it. Let's say for the first case, that's CD. Where is the CD? What do you think the CD is? I would say CD is somewhere here. So this is your CD. This is your CD. So for calculation of the CD, we have to cut the section in such a way that your CD calculation is easier. How can you cut the section? That's easier to calculate. You can cut in this way. You can cut in this way also. I would cut that's closer to the support. I would cut in this way. Let me cut it in this way. Let us make a section in this way. Method of sections. MOS. So I would say there would be some reaction when load is moving. There would be a reaction AA. Then I cut the section. Let's cut this section. I would say I have this section in this fashion. I have this section in this fashion. There's some force here. We are having some force here also, and we are having some force. This is our unknown force of F. To highlight this one, our unknown of CD is this one. Let's say this is some force of F, and here there would be some reaction of upward reaction of some reaction A. Let's say that these 2 points are meeting at point Q. These 2 forces are meeting at Q. This is the point Q. So if I say summation of moments at Q equals to 0 for this case, then I can get the value of that F force in CD. Can I say that? I think so. Now, for the first case, that load is placed at joint A. If the load is at point A, and there would be reaction of RA, that's also equals to 1. If I solve for that, I would say your moments would be equals to 1 into what is this length up to the point Q? Can you tell me what is the length? What is the total length up to the point Q? If the theta is 45, panel length is equals to A. Can you tell me what is this length, total length from the support A? Can you tell me what is this length equals to? Can you tell me what this length is equals to? Is this 1.5? Is this 1.5A? Is this 1.5A? I think it's 1.5A. So I think it's 1.5A. So the problem was that the problem is the through type loading. That's loading is from the bottom of those on the bottom joints. Load is placed on those joints. We are saying this. That's what we call as through type loading 1. Load can be placed anywhere. Now for that, we say loading joints are A, C, D, and after that we have these also. Now, if we apply summation of moments at Q equals to 0, what do you think this value of ordinate would be? What is this length, total length? I would say this is 1.5 A, and this is some length of A. Now I would say 1 into 1.5 A, then we have one more that's in again anti-clockwise direction, so that's in this way. So then we have one more minus times F into some height of H equals to 0. So F equals to 0. So for the first case, that load was placed at support A, so your ordinate of ILD is equals to 0. So first ordinate is equals to 0, and we need to get the ordinate at the point C when load was at point C. Now the second case is that load is placed at point C. If the load is placed now at point C, let's say the load is placed at this point C. If the load is placed at C, can you tell me the reaction? Can you get the reaction A? Can you tell me what's the reaction A? Can you tell me what is the reaction A? I think the reaction A would be equals to total length is 5. Total length is 5, and reaction load is at 1. Load is at 1 of that. So reaction would be 4 by 5. Reaction would be 4 by 5. If the load is at C, it's at A from capital A, and from the other side we have 4 times A. So reaction would be 4A by 5A. So finally 4 by 5. So reaction would be 4 by 5. Then I apply that moments, that clockwise 4 by 5 into length of 1.5A, and load is placed at this one's point C, and point C is at a distance of 0.5A from Q. Can I say that? So this is 1 into 0.5 into A, anti-clockwise. This is anti-clockwise about point Q. Then we have also one F, that's also anti-clockwise, F into H. So finally I would solve for F, and F ordinate would be equals to 0.7 A by H, 0.7 A by H, 0.7 A by H. We got one more ordinate, that's 0.7 A by H, 0.7 A by H somewhere here, 0.7 A by H, positive. Now third case is that load is placed at D. If the load is placed at D, what is the reaction we can have? Now load is placed here. load is placed here at 2a and 3a. So the reaction would be 3 times 3 by 5 of that, 3a by 5a. So reaction is 3 by 5. Reaction is 3 by 5. And there is no any other load in this section. There is no any other load in this section. Load is placed at D, though that means no load is in this section now. Only this reaction of 3 by 5. And I would say there is some moment developed 3 by 5 of 1.5a. Then minus times this one is not there. This one is not there. So I can get value of F equals to 0.9 a by h, 0.9 a by h, 0.9 a by h, 0.9 a by h somewhere here, 0.9 a by h. After that, so actually that we got those critical points. We got those critical points because your member was CD. If your member was CD, that's we had to get the critical points. One is your C and D. We got the ordinates and C and D. That means we have now joined them finally with a straight line, and that's your ILD. If I join this one to the end point, and if I join this one, and if I join those two also, so this is your ILD. This is your ILD. This is your ILD. ILD for CD. ILD for CD. Now, if you still want that, I want that load to be placed at this point. If I place the load here, I would say reaction would be 2 by 5th. I would say reaction would be 2 by 5th. And you solve for that, you would say 2 by 5th of that, 2 by 5th of that 1.3. That's 2 by 5th of 1 by 3, 2 by 5 of 1.5. That would be equals to 2 by 5 of 1.5. That's 0.6. That's 0.6 times a by h. That's 0.6. This would be 0.6. And if this is 0.6, that means the ordinate here is 0.6 a by h. After that, there's one more point we can have. We can apply the load here. I would say if the load was here, if the load was placed here, the reaction developed would be equals to 1 by 5th. Reaction developed would be 1 by 5th. 1 by 5th. And accordingly, I would get a value of 1 by 5 times 3. So that's 115 by 5. That's 0.3. That's 0.3. So 0.3 a by h. So by the symmetry, we can say this is also this would be 0.3 a by h. That we can directly also solve that. If we got the ordinate here 0.9, if this was the length of 3a, that means for the 2a this would be 0.6, and for the a this would be 0.3. Okay. From this side we have different slope. See, from this side we have different slope. From this side we have different slope. From this side we have different slope. If I extend this part, this would have been some that 1.4 a by h somewhere here up to this point. But this is not our goal here. This is not our concern here. Let's take this one as it's. Now, second case of the problem was that you need to get the ILD for QR. ILD for QR. Let's take one of those. ILD for QR. ILD for QR. So second case that for the QR you need to get ILD. Where your QR is, I would say QR is at the top. So this is your QR. QR is this one. So we need to cut the section in such a way that QR is easier to calculate. I would say if I cut the section in this way, then I would say this force is going meeting QD also in this at this point D. So I would apply summation of moments at the point D. So let's cut the section. I would say we have this section. There's some force here, and we have one more force downwards, inclined. One more is here, and they are meeting. These two are meeting here at point D, and I would say summation of moments at D equals to 0. And we have some unknown of F at height of H, and we have some reaction of RA. And now the thing is that load is placed at A. We now directly say if the load is at A, can you say what can you say that what would be the if the load is at A and this joint A, I would say reaction is A, reaction also 1, such that finally F is equals to 0. So if I draw the ILD for the first point, I would say ILD for the first point is 0. For the first point we have 0. For the first point we have 0, 0. After that we say you apply the load at point C, apply the load at joint C. Let's apply the load at joint C. Can you tell me the reaction? Is that 4 by 5? Is that 4 by 5 reaction? 4 by 5. And I had to solve for the moments at point D. Can you tell me what is the length, total length up to the point D? Is this equals to 2a? I think so. I think so. That's 2a. I would say this is a and this is 2a. I would say 4 by 5 clockwise for a length of 2a, then anti-clockwise 1 for the length of a, then anti-clockwise f into h, that's equals to 0. So f is equals to, you have that value, qr. We are solving for qr, yeah. So value is equals to 0.6 a by h. 8 minus 0.1. Is this 0.6? That's 8 by 5 minus 1. 0.6. A by h. Is it positive? Is it negative or positive? Negative. Negative value. This is negative value. Sorry. Positive minus negative. Is it positive? It should be negative. It should be negative. Yeah. See, is this one positive or negative? This one. This moment is positive or negative about point D. I think this is positive. I think this is positive clockwise about this point. So positive value. So positive value. That's why this finally it's coming negative 0.6 a by h. 0.6 a by h. So second ordinate is that negative 0.6 a by h. 0.6 a by h. A by h. Negative. So that means you have to join them by straight line. Okay. After that, we have the third case that load was placed at point D. Now the unit load is placed at joint D. If the load is placed at joint D, that means the reaction developed at point A, what that would be equals to? Would that be 3 by 5? Would that be 3 by 5? Would that be 3 by 5? This is 2A, this is 3A, and reaction would be 3A by 5A. 3 by 5. Reaction is 3 by 5. Okay, that means this is 3 by 5 of 2a, then this one is 0. So then finally I would say your value is equals to negative times 3 2s are 6. That's 1.2. That's 1.2. 1.2. So this is 1.2. 1.2 a by h. 1.2 a by h. And I would say we got those critical points for the QR, and I can join them. Now finally I can join this one also by a straight line. So this would be your ILD for your member QR. Now, if I still want that, I want to calculate if the load was at this one, then reaction would be 2 by 5. So accordingly, you would get 2 by 5. That's 4 by, that's 0.8. So you would get this ordinate as 0.8. You would get this ordinate as 0.8. And you can directly solve it by the similar triangles also. You can get this one also by similar triangles. And I would say this one would be 4.4 a by h also. This one would be 0.4 a by h. The load is placed at this one. So we got the ILD for this member also. Let's take the third case. Let's take the third one. That's member force. For the QC, we need to get the one ILD for the QC. ILD for the QC. Let's take the ILD for the QC member now. ILD for the member QC. Where is your QC? That's your diagonal member, web member. So your QC is this one. QC is this one. And load can be placed somewhere. Let's cut the section in this way. Let's cut this section. Let's cut this section now. I would say you have this triangle. After that, you have some force here. You have one more force here. You have one more force here. So what condition you can apply for this one? What is the condition you can apply? So there's some direction of RA, and there's some unknown force of F. This one is your unknown of FCQ, force in the member CQ, QC. So I would say there would be some theta. There would be some theta. So I would say your I'm going to apply summation of Fy equals to 0. So I would write some reaction A upwards plus F sine theta equals to 0. Now we have to place the loads. We have to place that unit load on different joints. So first case is that if I apply the load at point A, the reaction A is also 1. So finally F would be equals to 0. So for the first point, that load is at point A, so reaction would be 0. So ordinate is 0 also. So F is 0, so ordinate is 0. Second case is that load is placed at if the load is placed at point C, if I place the load at point C, if I place the load here at point C, unit of 1, if this is a unit of 1, that means what is the reaction we can have? Would that be 4 by 5th? Would that be 4 by 5th? I think that would be 4 by 5th. So I would say 4 by 5th, 4 by 5, upwards, then 1, then negative downwards of 1, then plus f sine theta equals to 0. And what's inverse of sine theta? 1 by sine theta, that's cosecant theta. So I would get a value of f equals to 4 minus 1, that's 0.2 cosecant theta. Minus times, is that minus times 0.2 cosecant theta? Is that positive or negative? I think this is positive, 0.2 cosecant theta. Why cosecant theta is actually d by h. This value is equals to d by h. Some diagonal would be there. If you have this triangle, some height would be there, some diagonal would be there. So this is d by h. So 0.2 cosecant theta, 0.2 cosecant theta. Zero point 0.2 cosecant theta. Now third case, that load is placed at joint D. Load is placed at joint D. What is the reaction we have? Reaction A, that would be 3 by 5. So the reaction would be 3 by 5. 3 by 5, and this one unit is not in this section now. The section in this section, there is no load of that 1 unit. This is out of that section, that's at joint D. So finally I would get 0.6. Then I get this 0.6, and it would be positive or negative. What is this value of? Would that be positive or negative? That's I think negative. 0.6 negative times 0.6 cosecant theta. 0.6 cosecant theta. So negative times 0.6 cosecant theta. So negative. And after that, once you got the critical points, you have to join them by straight line. You directly can join them now by a straight line. If you join them by a straight line, this would be your ILD. Now you can also solve it again if you vary now. If I vary the load now, if I place the load here, I would say reaction would be 2 by 5th, and accordingly you would get a value of 0.4. And after that, if I place the load here, you would get a reaction of 1 by 5. 1 by 5, that is 0.2. So 0.2 you would get here. 0.4 and 0.2. So this one would be 0.4. This one would be 0.2 cosecant theta. This is your ILD for your member. What you have, diagonal member is what was it QC? Diagonal member. For the diagonal member, you have this that variation. This is your ILD. Now final case of that's to get the ILD for member PA. So this is also diagonal member, but it's the end diagonal. Member PA is the end diagonal PA. So difference between other diagonal members and this one is that this member is having one triangle only. So if this is PA end diagonal, it's only connected to one triangle. It's a member of one triangle only. Now, if I talk about the QC was in this fashion. It was between two triangles. So we got two ordinates. We got two critical ordinates for the QC. For the QC, we got two critical ordinates. But for the PC, you will get only one critical ordinate. One of the ordinates is at the end support itself. We are going to see that one. So for the PA, we need to get. Let's take this one. Let's go for that. Let's go for the PA. Let's go for the PA. ILD for PA. So your concerned member is, so this is your PA, ILD for PA. So I'm going to cut the section in this way. That's very easier to calculate. I'm going to cut the section in this way. So I would say there will be some reaction. There is some reaction RA, and we have this unknown of F. There's some theta, and we have some force also here. We don't care about that. If I apply that summation of forces in the y direction equals to 0, that means I'm going to solve for that. I would say your reaction A, there is some reaction A, upwards plus F sine theta upwards equals to 0. So this is the procedure for that. So let's go for the case one that load was placed at A. If the load is placed at A, if the load is placed at joint A, can you tell me what's the ordinate we have? If the load is placed at the joint A, if the load was placed at the joint A, and what's the reaction we can have? Reaction would be also 1. So I would say 1 plus minus 1 and then plus f sine theta equals to 0 equals to 0. So f equals to 0 for the first point that load was placed at the joint A. So first ordinate is 0. Then second case is that load is placed at C. Now load is placed at C. Let's say load is placed at C. What is the reaction we have? What is the reaction we have? What is the reaction we have? I would say reaction is equals to 4 by 5. Is the reaction 4 by 5? I would say that 4 by 5 upwards plus f sine theta also upwards. F sine theta also upwards. So finally negative value of minus times 0.8 cosecant theta. Can I write that? Minus 0.8 cosecant theta. Minus 0.8 cosecant theta. Minus 0.8 cosecant theta. 0.8 cosecant theta negative. So once we got those two critical points in this member PC, PA, then we have to join this by the straight line. So this is your ILD. You can join them. Finally, this is your final ILD. Now I have to see whether this is correct or not. Let's take that third case. Load is placed at D. Load is placed at D. If the load is placed at D, what is the reaction we have? The reaction would be 3 by 5. So accordingly, you would get 3 by 5. So 0.6, 0.6. And finally, if the load is placed at this one, so reaction would be 2 by 5. So that's 0.4. And finally, if the reaction load is placed at this location, and you would get reaction of 1 by 5, that is 0.2 ordinate. So 0.2, 0.4, 0.6. So this is 0.6, this is 0.4, this is 0.2 cosecant theta. So this is your ILD for your PA. So once you got the two critical points, then you have to join the straight line, them by a straight line. So you join those, and this is not our critical point. That means here the value is 0. If the load is placed here, it would be 0. You have to just see which of these the member if there is some member, you have to see, is there any triangles it's connected with? I would say if this is your member, you have to see what are the joints, possible joints. We have possible joints. We have 4 possible joints for this one, and you have to see then what is the load possibility. Is the load passing from the top? That's if the loading is deck type, then we have to see on the top 2. If the loading is a through type, for the through type you have to see bottom 2. Then if you got the two critical points ordinates, then finally you have to join them up to the end line by straight lines. Whatever the variation would be, then you have to join them. Similarly, if you have bottom or top member, it might be having some triangle. Now if the load is placed at the top side, so we have two critical points. Now we have to see the values at these two joints. Now if the load is from the bottom side, I would say you have only one critical point. You had to, once you got this value, then you have to join them by a straight line. This is your ILD. Let's say whether we have any other problem left. So we have one more problem. That's loading is deck type. Loading is deck type. So you have loading of deck type, and the truss is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 panels we have. 6 panels. 1, 2, 3, 4, 5, 6. Then we have this member. We have these supports A and B. Supports A and B. And this is your PQRS. And the loading is mentioned that it's deck type loading. Deck type loading. That means loading joints are these. These are your loading joints. Loading joints. So load is passing from these. Load is 1 unit loading is from the top side, and we have to join them. We have to join the members, also those diagonal members. So finally, it looks like a N-type truss. N-type truss. Then after that, you have to reverse it. You have to reverse it. You have to reverse it. So this is your N-type. So let's say the panel length is A. Let's say the panel length is A. This is panel length of A, and height is equals to H. Height is equals to H. And theta, we can say theta is 45. Theta is 45. And I would say we have some diagonal of. If theta is 45, that means perpendicular H is also equals to A. And this is A. This would be root 2 of A. Now we need to get the ILD for member SE, ILD for member AC, SE, and QC. AC, SE, QC. Let's go for the first one, that's AC. Let's first copy this. Let's copy this one first. Okay. Now, first case is that loading that member AC. What is the member AC? We forgot that from the bottom side. Let's say that we have AC, DE. So for the first case, that member is AC. If the member is AC, member is AC, so this one. Sorry. So member is AC, so this one is your AC. Now, how can you cut the section such that less number of members are cut, and your AC calculation is easier? That means you have to cut the section that's in this fashion. So I'm going to cut the section in this way. So we have this section now. There's some force in this member F AC, so I would write this as a force of F. And this one we don't care about what is this value. And we have some reaction here also. There's some reaction. And first case is that when I place the load at the point A. Let's place the load at the point A. So let's have the ILD. I would say when I place the load at point A, what is the reaction we have? Can you tell me the reaction? If I place the load, load at A, actually the loading is deck type. So if I place the load here at P, that means the reaction developed at A would be equals to 1. If the reaction developed at A equals to 1, I would say there's some reaction of 1 upwards, and that would be balanced by this one. That would be taken by this member that's along the vertical. If I apply that summation of FH equals to 0, can I get F equals to 0? There's no one to balance the horizontal. I would say F equals to 0. So there is no horizontal force, so F equals to 0. So for the first case, I would say F equals to 0. Now you take the loading at joint Q. What is the reaction we have when the load is at joint Q? Would that be we have six panels. L equals to 6A. We have 6 panels, 1, 2, 3, 4, 5, 6. So I would say reaction would be 5 by 6. Reaction is 5 by 6 when loading is at. Second case is that when load was at. You can write also that load was at C. Then reaction is equals to 5 by 6. If the reaction is 5 by 6, what that means that would be taken by this member that's here. That would be taken by this member. So horizontal would be 0. So for all values of, so I would say finally, if I say for all values of loading at all those different joints, your force that ILD would be 0. So this is your ILD for member AC. So 0 force for all loadings. So this is your ILD blank. 0 ILD for member what you call as AC. Second case, member QC. Let's go for member QC. Member QC. Member QC. What is the member QC? This is A, B, C, D, E. So QC is this member. So this is our QC. Now we have to cut the section such that you have less number of unknowns. Why you can cut? If I cut the section in this way, that means more number of forces we have got. If I cut this in this way, so less number of forces we have. So let's have that one. Let's take that one. So let's cut the section for the QC. Where is the QC? Yeah, let's have this one. Let's cut this section in this way. So if we cut this section, I will be showing that section in this way. This one. After that, we have some force here, and from this side we have some force here, and we have some force here also. So So these two forces are horizontal. So we have to apply, I think, moments summation of forces in y. I have to see whether summation of Fy is equals to 0. I have to see, because other two forces are horizontal, so there is one option that you have to say I had to apply that summation of Fy. And there is some horizontal, there is some vertical reaction Ra. So for different loads, for loading at different joints, accordingly we can get the ILD ordinates. Let's take the first point, that loading was at point A. If the load was at point B, if the load is at point B, what is the reaction A? Is that also equal to A? If the reaction A equals to A, if the reaction is also 1, if the reaction at A is equals to 1, what is the ordinate we can have for the member QC? For the member QC. For the member QC. See, you have to show the load also. You have to show the load also, because remember, because you are not cutting the point B, you have to apply the load here. So when the load is at point B, the reaction developed was some 1 unit, and it might be transferred from this member, or it might be transferred from this member, but we don't care about that, where is the load path going. We are not cutting those sections, we are not cutting those members P and PC. We are calculating for QC for now. We have to just show the external loads, where the external loads and reactions would be. So I would say the external load was placed at point B, and same value of that has developed as a reaction at point A. Now that means, what is the force in the member QC? Can you calculate? I would say some reaction plus some F equals to 0. So I would say some F would be there. So if I say this is some general values, so based on this one, I would say 1 acting downwards plus 1 acting upwards plus F acting upwards equals to 0. F equals to 0. F equals to 0 at this point. When load was placed at joint B, that means reaction developed in member QC. That means member force QC is not having any force when load was placed at P. So second case, load is placed at Q. Now second case, load is placed at Q. Now load is placed at Q. Can you get the reaction? What's the reaction at A? I would say the reaction would be 5 by 6. The reaction is equals to 5 by 6. Would that be 5 by 6? I think so. Reaction would be 5 by 6. Treated as a simply support beam, you are placing load here, A 5A. This is your load of 1. Then this is your 5 by 6 of A, 5 by 6. Okay. So I would say the component would be 5 by 6. Finally, I would say the value would be 5 by 6 directly. I would say 5 by 6 upwards, then plus F upwards equals to 0. F equals to minus 5 by 6. Minus 5 by 6. That's also equals to insert some sort of that minus B by L. Minus B by L. Some sort of minus B by L. Some sort of minus B by L. We would see that also. So minus 5 by 6. Minus 5 by 6. And let's take one more case. Actually, this is the entire, you can now join those. Once you got the two critical points, you can join the ordinates now. Because why these two are critical points for this one? Why these two are critical? Now, because you see that where is the member QC? What is the member QC? This is your member QC, okay? What is the triangle it's having? What are the triangles it's having? So it's connected with two triangles. That are in this fashion. Okay. Now, if the loading is deck type, can you tell me what are the critical joints? Loading is deck type. That means critical joints are this one and this one. These two, these are not critical. That means we don't care about this joint now. We don't have to even calculate the calculations for this one. So this one is not necessary. So you need to say, if the load was placed at point P and point Q, if you got the ordinates, these two coordinates, you have to join them. But now finally, then after that, you have to join with a straight line. See, once you got this ordinate of 0, and once you got this one 5 by 6, there's no option. And this one that means this one would be 0. You have to join that by a straight line. This one by a straight line. This is the ILD. And still, if you want to calculate that, if the load was placed at joint K, if the load was placed at joint K, I would say reaction would be 2 by 6, 4 by 6, and finally you would get 4 by 6 value here. 4 by 6. Similarly, this one would be 3 by 6. This is 2 by 6. This is 1 by 6. This is 0 by 6. So 1, 2, 3, 4, 5, 6. So finally you would get same values as is. Okay, this was easy. QC was easy, I think. And if I extend this part, if I try to extend this part up to the end, what is this ordinate we can have? That's 6 by 6. We can also say this is value of that this is unit of 1. So total unit of 1, similar to that of a reaction. But because we have that critical points, so we need to join only those critical points. So this is your diagram, that ILD for member QC, negative diagram. Okay, we got this one also. Do we have left any other thing? SE. Where is the SE? So SE we need to get the SE. We need to get the SE. So let's go for the SE. SE, where is the SE we had? Yeah, SE is here. We need to get the SE. This is A, B, C, D, E. So SE is this one. So why you can cut the section size that you have less number of forces. If you cut it in this way, we got 1, 2, 3, 4 forces unknowns. Now if I cut it, there is one possibility that I can cut in this way also, we can get 4. So if I cut one more possibility of that, if I cut it in this way, so I can get only 3 forces. If I cut it in this way, I get only 3 forces. So there's some force here, there's some force here, and there's some force in this one, F. Let's call this one as force F. That's our constant force. So I would say that you have some reference line of ILD. This is some ILD reference line. Now once I cut this section, so our final section would be, diagram would be some sort of, final diagram would be some sort of, let's remove this part now. Let's try to erase it so that we can see what's the diagram we can have finally. Let's see whether we got something. So this is our section finally. Or we can take one, you can take this one. Either you can take this section or you can take this one. So there will be some force in this one, and from this side also there will be some force, and our consonant force is this one, force in the member F, that is SE. So we have this force of F. Now for this one you have this ILD reference line. I would say let's place the load at the first location of B. What is the reaction we have? Can you tell me the reactions? Because we are cutting the section. In this one we have entire structure also. We have the entire structure. When the load was placed at this location, unit load of 1, the reaction developed is equals to 1. Okay, reaction is also equals to 1. So what is the reaction here also? That reaction equals to 0. Now if I apply that, see, I cut the section such a way that these two are horizontal and this one is vertical. So I had to apply that summation Fy is equals to 0. That which implies that if once I got the that load was placed at a point B, 1 downwards, then I got a reaction of 1 upwards from A, and we have horizontal. That reaction at B equals to 0. Reaction at B equals to 0. And we have some force of F upwards equals to 0. So force finally equals to 0. For the first case, force equals to 0. Force equals to 0. So now second point is that second case, loading is placed at joint Q. Loading at joint Q. What is the reaction we have here? Is that 5 by 6? And that one would be 1 by 6. 5 by 6, 1 by 6. So if I say we have downward loading of -1, and this one is your 5 by 6 upwards, and this is 1 by 6, and there is some F equals to 0. So finally F is also 0. Can I get that F equals to 0? F equals to 0. Now actually we had only 3 critical points for this one, because once your member is F, that's SE, if this is your member SE, loading is placed at those joints from the deck side, because loading is deck type loading. So we need only these 3 critical points actually to calculate. I had to just calculate these 3 critical points. All other points would be 0. All other points would be 0. Similarly, if I take that loading placed at R, If the loading is placed at R, unit load of 1, place it at R, reaction here would be 4 by 6. This reaction is 2 by 6. I would say -1 downwards, 4 by 6 upwards, 2 by 6 upwards, F equals to 0. So F equals to 0. F equals to 0. And if I place the load from this side, load of 1, the reaction here would be this is 4 by 6 and this one is 2 by 6. And finally F equals to 0. F equals to 0. F equals to 0. And load place it here. If I place the load here, I would get reaction 5 by 6. This is 1 by 6. And I would get 5 by 6. This is 1 by 6. This is 5 by 6. F equals to 0. F equals to 0. Then after that, final joint that load is placed at this one. Load of 1 at this one. So reaction here would be equals to 1. This reaction equals to 0. I would say 0 plus -1 plus 0 plus 1 plus F equals to 0. So finally F equals to 0. So we got the critical points, all of the critical points. Now we only need to place the load. We only need to place the load at the joint, at this joint. When the load was placed at point S, if the load was placed at point S, at joint S, if the load is placed at joint S, what is the reaction we have? Can you get the reactions? Can you get the reactions? What are the reactions we have when load was placed at S? Because point S is at the midspan, I would say your reaction would be 0.5. Your reaction would be 0.5. Will that be? I would say, see, for this case, now the thing is that you have placed the load at the S, but in this section, S is not anywhere. S is not anywhere. So effect of that would not be there. You have placed the load at S. That's in the section, but that section is not there. So there is some force F here. There is some force here F, and reaction of 0.5, 0.5. I would say there is no in this section there is no vertical 1. So I would say 0.5 upwards plus 0.5 upwards and plus some F upwards. Some F is also upwards equals to 0. So F equals to -1. F equals to -1. So F equals to -1. So at this joint, F equals to 1. That's -1. Then we have to join those critical points. See, this is not a diagram. This is not the diagram because our triangle was that our member was this one, and we have to see the triangles. We have to see the triangle. This is your triangle. This is your joints. On these three joints, we have these three critical joints as our critical points in the ILD. So we have to join not by this one, but we have to join by this one. This is your ILD. Finally, you would say ILD would be in this way, that this is ordinate of 1 minus 1. This length is equals to 2a. So this is your ILD for member SE. Now one more thing is that now one more problem is that we can have let's take that through loading and total length is L equals to 4, 1, 2, 3, 4, 5, 6, 6a, and there might be some height of h, and your QD is diagonal member. So let's take the first case that diagonal member QD is there. Let's keep this one. Let's copy it. Drag. let's say we are dealing for the first case, that's your SE, and we draw some reference line for the ILD. That's ILD for SE. Let's talk about that first case of QD. Let's talk about the first case of that is QD. So this is our member QD, and I can cut the section in this way. If I cut this section in this way, I can show that section in this way now. I would say this is your reaction here, somewhat, some sort of reaction. There is some force here. We have one more force here also, and there is one more force of F. So this is our concerned force F. That's diagonal force along the diagonal. So this is your F. Now I would say load is that loading joints are A, B, D, etc. So load is placed along these joints. Now first case is that load placed at A. If the load is placed at A, 1 unit, reaction is 1, F is equals to 0. First case, F equals to 0. The second case is that load is placed at B. If the load is placed at B, here the reaction would be 5/6. Reaction is equals to 5/6, and we have some component of F. I would say 5/6 upwards minus 1 downwards plus minus F is also downwards, F sine theta. There is some theta, there would be some theta. Let's say the theta is some theta, and it's also provided that A equals to 5 meter, and H is also 5 meter. That means theta is 45. Theta is 45. Let's write it in terms of sine theta. So I got this one equals to 0. So I would say F equals to 1/6 of cosecant theta. 1/6 of cosecant theta. 1/6 of cosecant theta. 1/6 of cosecant theta. And finally, I had to solve that. You have that value of cosecant theta as √2. So √2/6 is that √2/6. √2 divided by 6. 0.2357. 0.2357, and this value is negative. If I see this value, it is negative. Finally, its final value is negative. So its value finally 0.2357. Cosecant theta is √2. Theta is 45. So 0.2357. 0.2357 negative. So 0.2357 negative. Join by straight line. We have to join by a straight line there. Okay. Now one more thing is that, see, one more critical point is that if you have this member QD, we have to see which of the triangles we have connected with this, and loading is placed at this point and this point. It is same as that if the loading is placed at this one and at this one. See, for the right angle triangles, it's not that different. There's no difference whether loading is at the top or loading is at the bottom. There's no difference because the joints are on the same line. Joints are at the same line, so that it does not have any effect. So our critical points is that one is your point of B, one is your point of D. So we got the point B. We need to get one more critical point, that's D. That means if the load is placed now at D, or you can place the load also at the R. If it's not mentioned that load, if it was not mentioned that where you can place the load, you can place either on the R or either on the D. So let's place the load along this line RD. That means the reaction developed would be 4/6. If the reaction is 4/6, and this load is outside the section, so I would say F sine theta. So finally this is 4/6 upwards. F is downwards, so you got positive value here. You would get a positive value of 4/6 cosecant theta. So that is equals to 9 point something, 0.9, some sort of 0.9, 0.9428, 4 times that initial value of 0.9428. So some positive value of 0.9428. 0.9428. That's 4/6 of cosecant theta. That's also 4/6. Cosecant theta is d/h, diagonal by that height, d/h. And after that, we can now directly we have a direct relation. If the load is placed here, I would say reaction is 3/6, and you would get the value here 3/6 cosecant theta. Load is placed here, that means reaction is 2/6, and you would get a value of 2/6. Load is placed here, you would get reaction of 1/6, and there is no change. You would only get 1/6 of cosecant theta. So it's a linear variation now. After that, there is a linear variation. That's all positive values. So here would get if this was 4/6, this would be 3/6. This would be 2/6. This would be 1/6. of cosecant theta. And because the slope has to remain same, so that slope has to remain same. Slope has to remain same. This is your variation. And after that, from this side, you have to join that. You have to join also that one. Then finally, these two critical points, this one and this one, that this is your critical point 1, this one is your second critical points. Once you got these two, you have to just join them. Once you join them, then you connect with the ends. So that's your ILD. So I would say the equation for this one is actually we have that simply support beam. You have that section at x. We say that the shear force from the bottom is equals to ILD ordinate is x by L. This ordinate is L minus x by L. Similarly, for this case, I would say this value is equals to x by L, and this one is equals to L minus x by L. And I say that general equation that you can have that x value, but in the opposite direction, that this one is your x by L. And you have one more factor here, because the member is diagonal, so you have to multiply this factor of d by h. You have to multiply this factor of d by h. That's the cosecant theta. This part is cosecant theta. So x by L is so your value of x is varying. For this point, you can say this is x by L d by h, where your value of x is this part x. And similarly for this one, your value is x by L d by h. This is your variation. And for the first one, because we said this one is your a by L, so for this one you have to go x in this direction. Okay, we got this one. Now one more is that SE. For the SE we need to get. For the SE, we already got it for one case, that loading was from the top. Loading was from the top. That's loading was from the top. When the loading was from the top, so we had 3 critical points. Now one more thing is that now if the loading is from the bottom, if the loading is through type. Now if the loading is through type, we see we have this member SE. It's having 2 triangles. It's having 2 triangles connected. For the deck type loading, we had 3 critical joints. But for the through type loading, we have only 1 joint, that's E. So we have to place the load here only. If you got this critical point, then we have to see what is the equation for this one. So this is your point E. Let's have that point E. So we need to cut the member SE. We have to cut the member SE. Let's try to cut the member SE in this way. As that of earlier case, we cut that earlier also. Let's try to cut that again, same way. Okay. Let's go. So this is our configuration now. This is our configuration. Let's have that reference line, ILD. I would say for all values of that, you place load. Let's say you place the load at joint, let's have a different color. You place the load at joint A. The reaction A would be 1, and there would be some force in the member F. Let's say this is some force F. There's some horizontal in this one. We don't care about those horizontals. Let's apply summation Fy equals to 0. That means there's some reaction here. That means A plus B and some vertical loading of downwards 1, then plus F equals to 0. So this is our general equation. So if I say what is this reaction of, and when load was placed at joint A, that means reaction was 1 plus 0 minus 1 plus F equals to 0. So F equals to 0. Similarly from this side, F equals to 0. Finally, I would say here also you would get F equals to 0. Here you also get F equals to 0 from this side also, from this side also. Now final thing is that when the load is placed at, when the final case is that when load was placed at E. If the load is placed at E, reaction is equals to 0.5, and this reaction is equals to 0.5. Once you got this reaction 0.5 and this one also 0.5. In the previous case also, when the load I placed the load at, in the previous case I placed the load at S, and the reaction was also 0.5. Reaction was also 0.5. But the section we had some section. In that case, the effect of that S was not there. We had already reaction 1 and reaction 2, and then we said there is some F here. But in this case, your loading joint is shown in the section itself. Your loading joint is also shown. That means this reaction is not anywhere. That means it's also shown in the section. So if I write the equation now, I would say 0.5 upwards plus 0.5 upwards, and downward 1 unit load, and we have one more, f equals to 0. So finally, for this case, f equals to 0. So that means your line is, ILD is a straight line. This is your ILD for SE when the loading is through type. So the difference between the first and second, this the ILD was for the first case, it was -1 when the loading was deck type, and in this case loading that ILD is 0 for the entire loading placed at different joints. So this is the ILD. Different problems we had related to ILDs by doing the performing the analysis. In the second one, in the next lecture, we'll be having ILDs by shortcuts. By performing those shortcuts, I'll be having that ILDs directly. We can directly solve those ILDs by those shortcuts. Let's end this class, and thank you.